Hello everyone. The title of this video is the Dirac delta function and Laplace transforms and examples of those. Alright, so I'm going to start off the video by explaining what a unit impulse is, a unit impulse function, and then from there define the Dirac delta function and what the Laplace transform of the Dirac delta function would be. And then I'll go into several examples, got I believe 3 examples of some initial value problems involving the Dirac delta function that I'll then solve using Laplace transforms. Alright, so let's start off by talking about unit impulses. Now, very often in real world applications, especially physical applications, a force is acted upon an object for a very brief period of time. Very brief. For instance, if you hit a golf ball, a force is enacted on the ball for a fraction of a second, and then it takes off. We could talk about springs, masses hanging from springs, and then maybe hitting that spring with a hammer at one instant or another instant, but for a very brief period of time. You could call this brief surge of force an impulse. Well, we're not going to the point of this video is not to actually look at physical applications, but I just want to point out where these might be used. So let's get into now what is the unit, a unit impulse function. So it's a piecewise defined function over the non-negative real numbers from 0 to infinity, and it's labeled by, this is the Greek letter delta, a little curly, almost like a lowercase d, but a little curlier. Delta sub a of t minus t sub 0. All right, now the value of a and t sub 0 are assumed to be positive here. Okay, they're both positive quantities. All right, and this function is defined piecewise. It's defined as 0 for values of t, from 0 to t sub 0 minus a. So from 0 up until a units before t sub 0, say time sub t sub 0, usually t will represent time here. No force, no value of 0. Then at t sub 0, and between t sub 0 minus a and t sub 0 plus a, so just in a very tiny interval from t sub 0 minus a to t sub 0 plus a, the value of the unit impulse function is such that we get a rectangle with an area of 1 square unit. Okay, so that's why the value is 1 over 2a, right? Because the length of this interval from t0 minus a to t0 plus a, that's 2a. So I need the height of this rectangle, right, to be 1 over 2a in order for the area underneath the curve to be 1 unit. And then beyond that, the value of the function is 0 again. Right, and so that way the integral from 0 to infinity of this unit impulse function, with respect to t, is 1. Right? The area under the curve from 0 to infinity is just the area under this little rectangle here. That's 1. Now you could also think of these impulses this way. Also, you could think of the unit impulse, the delta sub a at t minus t sub 0, in terms of unit step functions. So hopefully you recall from a previous video the Heaviside function or unit step function. Now I could set this up here to say, this is 0, and then I'm adding on 1 over 2a, but only beyond t sub 0 minus a, so this is times the unit step function at t minus t sub 0 minus a, like that. And then I take that away after t sub 0 plus a, so I subtract 1 over 2a times, the unit step function at t minus t sub 0 plus a. And again, the 0 is not necessary there. So you could also think, add to the note down here, you could think of these unit impulse functions delta sub a at t minus t sub 0 in this way, as 1 over 2a times, and then the unit step function at t minus t sub 0 minus a, then minus the unit step function at t minus t sub 0 plus a. Okay, you could think of it, these, again, hopefully you recall what these unit step functions are. Alright, so now we get to the discussion of what's called the Dirac delta function. And the Dirac delta function is just what happens as the value of this a approaches 0. So if you think about it, for these unit impulse functions, as a approaches 0, these two values, the t0 minus a and t0 plus a, will get smaller, will get closer and closer to t0. And if these are getting closer and squeezing into t0, remember, I need the area of the rectangle to be 1. The value, the height of this rectangle, it'll get thinner and thinner, but it'll also get taller and taller and taller and taller. And if you think of 1 over 2a, as a approaches 0, gets really, really tiny, this is getting really, really large, and it should be approaching 0 from the right, from the positive side. So that's what happens. That's how this Dirac delta function is defined. All right, so on my next page here, I've got what's called the Dirac delta function. Now, I might be mispronouncing this. I apologize if you heard it some other way. Please, think of it that way when you say it to yourself. The Dirac delta function is just simply delta of t minus t sub 0 for some positive t sub 0, no subscript. All right, and what it is as I mentioned, it's the limit as a approaches 0 of our unit impulse functions from the previous page. And like I was saying, you could think of it this way. The Dirac delta function at t minus t sub 0 is defined this way. It's this limit, and the limit approaches infinity when t equals t sub 0, right? And the limit approaches 0 everywhere else. So again, this is not so much, so here's say t sub 0, and we get in, it's like a very sudden large impulse, 0 everywhere else, and then at t sub 0, just, the limit approaches infinity, it shoots up. So a sudden impulse at an instant, right? Also, the integral from 0 to infinity of the Dirac delta function is defined to be 1, just as it was for all the impulse functions, right? This is always 1, so this is a constant. This is a constant here. So even as a approaches 0, this remains constant. Right, so the integral from 0 to infinity of the Dirac delta function with respect to t is also 1. And then here's the thing I want to really get into, is for these values of t sub 0 that are positive, the Laplace transform of the Dirac delta function at t minus t sub 0 here. Again, you could use our unit impulse functions from the previous page. Take the limit as a approaches 0 of the unit impulse functions, and you may remember what the Laplace transform of the unit step functions were. So you could actually use this and the Laplace transforms of the unit step functions to figure out, hey, this is going to be equal to just e to the negative s times whatever t sub 0 is. All right. So I put little stars on this, little asterisks, because this is going to be huge for the rest of my examples. All right, so like I said, this kind of function comes up in physical applications where a force is enacted on an object at a very brief moment, at an instant. All right. So like I said, like a golf club, like a hammer on a nail. All right, those are just two simple examples. I'm sure there are plenty of others that I'm not saying right now. Okay, so let's keeping this in mind, all this stuff. Let us now go to some examples where I'm going to be solving some initial value problems. But the differential equation involves this Dirac delta function. All right, so I'm asked to, in this example and all the examples in this video, use the Laplace transform to solve the given initial value problem. Now, if you've seen videos from me before where I used the Laplace transform to solve an initial value problem, an IVP, I'm going to be going through the same procedure. You take the Laplace transform of both sides, solve for the Laplace transform of y, and then take the inverse Laplace transform. So I'm assuming some things here. I'm assuming you know what the Laplace transform of a derivative is. I'm also going to be assuming that you know the second translation theorem, for Laplace transforms, for translation about the t-axis. Again, that was discussed in a prior video as well. So I'm going to be assuming some sort of previous knowledge here. All right, so I have y prime minus 3y equals, the Dirac delta function at t minus 2. So this just means that some impulse occurs at time 2 seconds or 2 minutes at t equals 2. All right, this may be some sort of outside force, driving force in a spring problem or whatever. I don't know. Again, this probably isn't coming from a spring problem. This is just some made-up equation. But you'd see something like this where a sudden impulse, a sudden burst of force, a driving force is occurring at time equals 2. And that's it, right? And 0 everywhere else. Okay. So, first step, and off to the side here I'll say we'll let the Laplace transform of little y of t. I'm going to call that capital Y of s. All right. So keep that in mind. Alright, so here, take the Laplace transform of both sides, and I'm using the linearity, so we have the Laplace transform of y prime minus 3 times the Laplace transform of y equals the Laplace transform of the Dirac delta function, more curvy, at t minus 2. Alright, so over here, remember the Laplace transform of y prime was s times the Laplace transform of y, so s times y of s, minus, and then the value of y at 0, which is given in our initial conditions to be 0, so I'm not going to write that in the next line. Then we have minus 3 times the Laplace transform of y, I said we're calling capital Y of s, equals, and then here, from the previous page, right, the Laplace transform of the Dirac delta function at t minus t sub 0 is e to the negative s times that t sub 0. So here, t sub 0 is 2, the time where the impulse occurs. Right? So the Laplace transform of this Dirac delta function at t minus 2 is e to the negative 2s. Negative s times 2, negative 2s. Okay. So now, we solve for y of s here. And don't forget the initial condition is 0, so I don't really need that y of 0 there. Right, y of 0 is 0. Sorry. And if I solve for y of s, Right, this Laplace transform of little y of t, our solution. Well, both of these have y of s in common. I would factor that out. There'd be s minus 3. I'd divide. So we'd get 1 over s minus 3 times e to the negative 2s. Now there's a reason why I'm writing it this way. Hopefully you recall the second translation theorem for Laplace transforms. And if you don't, I'll try to refresh your memory here. 1 over s minus 3. Right, 1 over s minus 3 is the Laplace transform of e to the 3t. Right. But then it's multiplied by this e to the negative 2s. So, again, hopefully you recall this, that the Laplace transform of f of t minus, I'll use t0 just to stick with what we had earlier, t minus t0 times the unit step function at t minus t0 was equal to e to the negative t0s, or s times t0 times f of s, where f of s equals the Laplace transform of little f of just t. All right. So our little f of t here is e to the 3t, and this was the second translation theorem. All right. So what I'm saying is, when we do the inverse Laplace transform, get little y of t, this is the Laplace transform of e to the 3t, of e to the 3t, but with t replaced by t minus 2, and then times the unit step function at t minus 2. All right, so this is inverse Laplace. This would be e to the 3 times, and then instead of t, got t minus 2. And then this is multiplied by the unit step function at t minus 2. Okay, remember, anything with this unit step function attached can be written as a piecewise defined function as well, and I'll get to that in a second. All right, but first I'll box this. This is a perfectly valid way to describe the solution of our differential equation, of our initial value problem. Now you could also again re-express this, these functions involving unit step functions. You could express this way, right? Y of t equals, and this will be defined differently, to being from 0 to 2 and then beyond 2. So if t is between 0 and 2, remember the value of the unit step function here between 0 and 2 would be 0. So you'd have 0 times, e to the 3 times 3t minus 6 if you distribute the 3. And then for t greater than or equal to 2, the value of the unit step function would be 1. So it'd be e to the 3t minus 6, or 3 times t minus 2. Okay. So same thing. Right? These are representing the same kind of function. Right, and that's really it. Right, I hope so. You're going to have to remember, the second translation theorem, which was again this thing in the bubble here, and also the Laplace transform of the Dirac delta function, which is stated on the previous page. All right, so let's do that again. I'm going to do that several more times. I got two more examples. Alright, so my next example is a second order equation. And we're asked to find, what's y of t. We have y double prime plus y equals, the Dirac delta function at t minus 2 pi. So that t sub 0 is 2 pi here. And then y of 0 is 0. Y prime at 0 is 1. Alright, so first, the Laplace transform of both sides. So I got the Laplace transform of y double prime plus the Laplace transform of y equals the Laplace transform of t minus 2 pi. Now this, and hopefully you remember the Laplace transforms of derivatives, this would be s squared times y of s, where y of s is the Laplace transform of little y, minus s times y of 0, which is going to be nothing, minus y prime of 0, okay, which is going to be 1. Then plus the Laplace transform of y is y of s equals, and then one more time here from this page, the Laplace transform of the Dirac delta function at t minus 2 pi be e to the negative s times 2 pi, or e to the negative 2 pi s. Okay. Well, replacing all the y of 0, y prime of 0 with the initial conditions, right? This is 0, this is 1, and solving for y of s, I would get the following. So step 2 is solve for y of s. Well, we'd have 1 plus e to the negative 2 pi s. Right, adding 1 first, and then I'd factor the y of s out from both of these terms. And you'd have s squared plus 1. So times, now again, there's a reason I'm writing it this way. 1 over s squared plus 1. In fact, you could write it this way as well. This is 1 over s squared plus 1 times 1 plus 1 over s squared plus 1 times e to the negative 2 pi s. And you see this one here, I'm going to be using the second translation theorem to state the inverse Laplace transform. This one's not so bad. Alright, so then we take inverse Laplace transforms to find little y of t. Now the inverse Laplace transform of 1 over s squared plus 1, that should be hopefully something you remember pretty easily. That'd be the sine of t. Right. The inverse Laplace transform of 1 over s squared plus 1 would be the sine of t. And then I've got the sine of t again, but I'm going to replace t with t minus 2 pi and then multiply by the unit step function at t minus 2 pi. So this is plus, through the second translation theorem, the inverse Laplace transform of this would be the sine of t minus 2 pi times the unit step function at t minus 2 pi. Alright, and this is totally valid. Totally valid. The only thing is, we could simplify this a bit. The sine of t minus 2 pi would just be the same thing as the sine of t. So this is the sine of t plus the sine of t times the unit step function at t minus 2 pi. And again, both are equally valid solutions to this initial value problem. And once again, I could, if I wanted to, write this as a piecewise defined function, right, and it involves some unit step function here. So I could also express the solutions this way: y of t equals, and this is going to break up to values from 0 to 2 pi, and then beyond 2 pi, right, where t is greater than or equal to 2 pi. Now for values of t from 0 to 2 pi, not including 2 pi, the unit step function has a value of 0. So I just have sine of t, y equals sine of t there, in that interval. But then for values beyond 2 pi, right, the value of the unit step function is 1. So you have sine of t plus sine of t. You have 2 sine of t for values, of t beyond 2 pi or greater. And this is totally valid as well. This is the same function as this, but only this is written with the unit step function involved. Okay, so pretty much the same thing. All right, and then I've got one final example involving, where the differential equation involves this Dirac delta function. And it's another second order equation. It's, again, very similar. And if you remember your second translation theorem and how the unit step functions are involved with that, then you should be fine. Then none of these should be too terribly difficult. All right, so I'm going to go a little faster here. The Laplace transform of y double prime is, again, s squared times y of s minus s times y of 0 minus y prime of 0 plus 2 times the Laplace transform of y prime. So I'm going to distribute the 2. That'd be 2s times capital Y of s minus 2 times y of 0. All right, just distributing the 2 over that. And then equals the Laplace transform of the Dirac delta function at t minus 1 is e to the negative s. E to the negative s times 1. E to the negative 1s. All right, so I've taken the Laplace transform of both sides. I put in my initial conditions. Y of 0 is 0, so this is 0 here. That term's gone. This is 0 as well. That term's gone. And then y prime of 0 is again 1. All right, so I'm gonna add 1 to both sides. So we have 1 plus e to the negative s multiplied by, take all the terms with y of s in there, you have s squared plus 2s. Let me dividing by that. So y of s equals 1 over s squared plus 2s. And, I'll have that on its own, and then that times e to the negative s. So I want to know what function has a Laplace transform of 1 over s squared plus 2s. I'll do this in a different color. So I'll take this off to the side here. Now 1 over s squared plus 2s, that's 1 over s times s plus 2. And I can do some partial fraction decomposition here. This is some constant over s plus some constant over s plus 2. Multiply through by the denominators. You got 1 equals a times s plus 2 plus b times s. If s were 0, a would be a half. And if s were negative 2, b is negative half. Okay. Alright, so we're seeing that 1 over s times s plus 2 is half of 1 over s minus a half of 1 over s plus 2. And so the inverse Laplace transform, if I do the inverse Laplace transform of this expression, it would be half of 1 minus half of e to the negative 2t. This function would have that Laplace transform. Alright, so taking this term by term here, we have y of t equals, we have 1 over s squared plus 2s times 1, so there's the inverse Laplace transform. It'd be 1 half minus 1 half e to the negative 2t. Alright, that's what I get when I do just the inverse Laplace transform of this first term. And then I'd have 1 over s squared plus 2s times e to the negative s. So I need the second translation theorem here. Well, that would be the same function where t is replaced by t minus 1, and then it's multiplied by the unit step function at t minus 1. So it would be plus half minus half e to the negative 2 times the quantity t minus 1, and then times the unit step function at t minus 1. And there you go. This is the solution of our initial value problem of this differential equation involving the Dirac delta function. Alright, now let's, just as before, I'll do the same thing here where, I'll leave it to you. You can write this as a piecewise defined function, right? For it'll be one thing when the values of t are from 0 to 1, not including 1, and it'll be a totally other expression when the values are from 1 or greater, right? Based on this, the unit step function there. But yeah, this is totally valid as the solution for our differential equation. Wonderful. All right. So, again, hopefully watching me go through these few examples, I had 3 of them here, 3 initial value problems involving the Dirac delta function. Hopefully watching me go through those examples help you out when you're working on similar problems. And thank you very much for watching.